Hi, everyone. Today I'm going to be talking about investigating relationships between two variables. This is covering the first part of chapter 16 in your textbook. And I'm going to go over cross tabulations in particular. So first, you can describe the relationship between two different variables in a number of different ways, some of which you're probably already familiar with. So we've been speaking before about talking about the direction of the relationships that we expect, whether those relationships are positive, do they increase and decrease together, or are they negative? As one variable increases, the other variable decreases. We've also alluded to the form of the relationship. We've talked mostly about relationships being potentially linear in form. And many times, as we'll see as we move forward, we assume linear relationships in political science. While that might not always be the case, relationships can be in different forms as well. And then something also that we're going to be speaking about is the strength of the relationship. So say they are, moving together in some sort of positive or negative linear pattern. How strong is that relationship? How consistent is that relationship? And then later, our next step is we're going to move on how we can determine whether a relationship between variables is causal. So again, that's our end goal. But what we're going to be speaking about this week is the correlation between variables. How do they vary together? And then later, we'll move on to trying to establish causal relationships between variables. So this is just an example from your textbook. We could see what a relationship would look like in terms of its form, a linear relationship, and also in terms of its direction, whether it's a positive or negative relationship. And you guys can see how this is charted on an XY axis. You might recall in the past that I've talked about labeling our independent variables as X, pertaining to that X-axis, and our dependent variables as Y. So that's an example of what that would look like. So each dot would represent a particular respondent or country, whatever our unit of analysis is, where it would fall on both the X-axis, one particular independent variable, and the dependent variable. And then this next slide is showing us kind of the difference between what we would consider to be a strong positive relationship versus a weak positive relationship. So we can see that one is more consistently across that linear line, while the second one is not. So we can kind of begin to speak about the direction, the form, and the strength of our relationships by plotting them in some examples. But of course, how we look at the relationship between our variables can differ across different research designs. And we speak about having different measures of association that allow us to talk about the extent to which two variables are related. And it's important to note that each level of measurement has different measures of association. So as you might imagine, there would be examples where plotting your data on an XY axis would not be particularly appropriate. So for instance, if your key independent variable was something like gender or some sort of categorical value, instead of being ordinal or ratio, you could maybe start to picture how it wouldn't be appropriate to assume a linear relationship like in those examples before. So again, that's why I keep stressing to you guys the importance of being aware of level of measurement. So for the different levels of measurement of your dependent variable and your independent variable, different types of statistical procedures will be appropriate. So this is drawn from your textbook. And I just want to look at this table for a second and kind of give you some examples of what I'm talking about. So remember my example from speaking about statistical inference. I walked through an example of differences in receiving the death penalty, the dependent variable, versus gender, which would be what we'd call a dichotomous nominal variable. So looking at the first row, a quantitative dependent variable, that in this example is meaning something like ratio or interval, with the dichotomous independent variable, something that would make sense to do would be a difference of means and difference of proportions test, which was very similar to what I was doing. Drawing your attention to the bottom of the table, the last two rows, we can see that the procedures suggested are regression, which is what, of course, we've been seeing a lot of in our articles for class, and what's going to be kind of our ultimate goal for our research projects. And what you might notice is that there's two different types, linear regression versus logistic regression. And if you look over to the first column, you can see that our choice is dependent upon the level of measurement of our dependent variable. So if you have a dependent variable that's ratio and maybe even ordinal level, it would probably make sense to do a linear regression. But if you had a dichotomous dependent variable, say for instance something like voted or did not vote, a linear regression model wouldn't make sense, and you would do logistic regression. So I don't expect you to understand what those things mean yet, but I just want to point out that the choices you make moving forward are going to be heavily dependent on the level of measurement of your variables. So today what I want to talk about is a particular measure of association that's very intuitive if you have nominal or ordinal level variables. So we'll move later into more for the ratio level, but something that's really intuitive, I think, if you have interesting nominal and ordinal level variables that you want to look at the relationship between, I would suggest doing a cross tabulation. And a cross tabulation is very similar to a frequency distribution. But what it does is display both the joint and relative frequencies of two categorical variables. So those are probably unfamiliar terms. So I'm just going to go ahead and talk about how we make one and what it looks like, and then you'll see what I'm talking about. So first what you would do is you would separate your variables into groups based on their values for a particular independent variable of interest. And then next, for each group of that independent variable, you compute the frequency of falling into each level of a particular dependent variable. And then looking at these joint frequencies, you can decide whether they differ from group to group, and if they do so, in some meaningful way. So again, I think it makes most sense to just take a look at one to see what I'm talking about. So first of all, when reading a cross tabulation, the columns are always going to be the independent variable, and the rows are going to be the dependent variable. So our independent variable in this example is gender. And you'll notice because the column totals for the independent variable are always going to equal to 100%. In this example, they were rounded up, but what I'm looking at right here are these column totals. And then our dependent variable is the partisan identification using this 7-point scale here. So how we would read the cross tabulation is that we could say of the individuals surveyed, 11.9% of men identified as a strong Democrat. 20.9% of females identified as a strong Democrat. And then we would, read it the same way as the way down. Just looking at the data, we can begin to think that there might be some sort of relationship going on between gender and partisan identification. So here's just another example of a cross tabulation. In this example, the columns are liberal, moderate, and conservative. So ideology on just a 3-point scale. And then the dependent variable is how often does the respondent pray? And we see the different options in the column. And so again, you see your column totals equal to 100%. And then when you look at the totals across the rows, we can, for instance, see at the end that 27.9% of respondents say that they pray several times a day. And so then again, how we would read this is that 18% of liberals surveyed said that they pray several times a day. So again, just practice in reading across tabulation. Okay, so how can we talk in a more concrete manner about what the crosstab is showing us? So what I want to do here is combine our conversation about the cross tabulation with what we talked about last week and statistical inference. So can we show a statistically significant relationship between variables using a cross tabulation? So again, simply we're asking, do the observed relationships reflect true patterns, or could they just be arising from chance? So what we're concerned with in terms of a null hypothesis with a crosstab is statistical independence. So the null hypothesis would be that there is complete statistical independence. And what does that mean? So the property of two variables in which the probability that an observation is in a particular category of one variable and a particular category of the other variable equals the marginal probability of being in those categories. Okay, so if you're like me, just reading that makes absolutely no sense. So I think what's the best way to go about it is just walk through an example together to see what statistical independence looks like. Okay, so I have a very simplistic example here. You'll see that my independent variable is gender, and I have male and female. The dependent variable, again, dichotomous, meaning two categories, and nominal, voted and did not vote. And then we have 300 people total that took this survey. So first, what we do is we calculate the probability of being male. So we see that there's 100 men who took this survey out of 300 total. So the probability of being male is 0.33. We then look at the probability of voting. Out of the 300 people who took this survey, 210 reported voting. It's pretty high, meaning the probability of voting was 0.7. And then what we do, we calculate what we call the marginal probability. So you'll remember that term from the last slide. The marginal probability is the two probabilities separate multiplied together. So 0.33 times 0.7 gives us a marginal probability of 0.23. Next, we compare the marginal probability to what we call the joint probability, the probability of being both male and voting. So that's where we look at the actual data here, and we see, looking at the first row, first column, that 70 males voted out of 300. 70 divided by 300 gives us 0.23. So in this example, our joint probability, that actual probability, matched our marginal probability. And what that's showing is complete statistical independence. In this example, gender and voting are statistically independent. Let's walk through one more example together. So another simple model where our independent variable is social class, just categorized as upper and lower class. And again, our dependent variable is turnout. So what we're going to do here is calculate the marginal probability of not voting and being in the lower class, and then compare that to the joint probability. So the probability of being lower class in this example is 150. That's the total, the total number if we're looking at the bottom of that third column. 150 divided by 300 gives us 0.5. And now we're going to look at the probability of not voting. So that's did not vote. So we're looking at that second row all the way across. 150 people reported not voting. 150 divided by 300 equals 0.5 is, again, of course, which gives us a marginal probability of 0.5 times 0.5 equaling 0.25. Now, let's compare that to the joint probability of being in the lower class and not voting. So to find that number again, we're in the second row, third column, 100 people. 100 people were in the lower class, did not vote. So our joint probability is 100 divided by 300, 0.33. So in this example, our variables are not statistically significant because we see that the joint probability is greater than the marginal probability. And again, it doesn't matter if it's greater than or less than, that would show direction, but just that it's different, that is showing that they're not statistically independent from one another. Okay, so we can see that they are in the last example that they were not statistically independent. But again, thinking back to what we learned last week, we want to be able to test that for statistical significance at a certain confidence level. So you remember in your example from the quiz that the test statistic that we calculated for the regression model was the t-statistic for the normal distribution. This is going to be the chi-square distribution, and we're going to calculate the chi-square test. I'm going to show you an example of how to calculate a chi-square by hand. I'm doing this because I wanted you to have a feel kind of for what the test statistic is doing. I'm not going to expect you to do this on your own, but just bear with me to get a quick idea of what this looks like. Okay. So again, the statistic used to test the statistical significance of a relationship in the crosstab. So we're going to be able to say, okay, are they statistically independent or dependent at a significant level? So of course, this is what's going to lead us to either accept or reject our null hypothesis, thinking back to last week, sorry. So a chi-square of 0 would imply complete statistical independence. And then I'm going to show you in a little bit if we have a chi-square different than 0, how to know whether it's at a statistically significant level or not. Okay, so this is the data that I'm going to be using to do my example. Again, you'll see that the independent variable is gender, and the dependent variable represented by our rows is opinion on gun control. And what you're seeing then here is those probabilities. So again, we could read it like 32.6% of men say that buying a gun should be a lot more difficult compared to 53.6% of women. Okay, so the first thing to do to test whether the differences we're seeing are statistically significant, the first thing we have to do is calculate what we call our expected frequencies. That's what's represented in this next table. And you'll see on the very bottom of the PowerPoint slide how I calculated these numbers. What the expected frequency is the row total times the column total divided by the total number of respondents. So, for instance, looking at the number under male and a lot more difficult, I'm looking at this 252.96. How I got that was I took this column total, 582, multiplied it by the row total, 522, and I divided that number by the total, 1,201. So again, just one more example. 269.04 under female. The expected frequency was calculated. This number was achieved by doing the 619 column total times the 522 row total and dividing by the 1,201. So an important first step is calculating all the expected frequencies. Then what we do is we take the difference between the observed and expected. So this might remind you a little bit of standard deviation in some ways. So in my first column, these are the actual observed frequencies from the cross tabulation. The second column are the corresponding expected frequencies. And then in my third column, you see I take the difference between the observed and the expected. In column 4, the next step is squaring those differences. And then the final step in column 5 is taking those differences squared and dividing them by the expected frequencies again from column 2. And then when those are all summed together, that gives us our chi-square. So in this example, our chi-square is 62.20. So definitely very much greater than 1, or 0, I'm sorry, which would suggest statistical independence. But in order to really know whether it's statistically significant, we have to turn to our chi-square distribution. And we need to know something called the degrees of freedom. This is something unique to this type of distribution. Well, it's also seen in other distributions, but you might recall we did not see it in the normal distribution, which was like that T statistic that we saw in our quiz. So the degrees of freedom is the number of rows minus 1 times the number of columns. I'm sorry, I reversed this in my example, but it doesn't matter. It's just multiplication. So we had 2 columns, you'll recall. That was the gender. And then we had 5 categories for the gun control, which gives us a degrees of freedom of 4. And then what I can do is I can turn to Appendix C in the textbook. Gives me the different values, which I'll show you in a second. I'll stop this screen share and try to share that with you. But anyway, if I look at this table and I want to be 95%, if I want to be 95% or 99% confident that there's a relationship between variables, I see that I would have to have a chi-square statistic of over 13.28. So mine is way above that. Looking at this chart, I can see that, I could be 99.9% confident that the variables are not statistically independent. So I can definitely reject my null hypothesis in this example. So I hope that makes a little bit of sense to you. Again, I'm not going to make you guys calculate that by hand. But I am going to show you an example coming up soon about how to do a cross tabulation and a chi-square statistic using the statistical software that I'm going to share with you guys. So now hopefully if you want to incorporate that into your own paper, you'll know how to interpret the chi-square and you'll have an understanding of what it means if it's statistically significant. Okay, thank you guys for listening. And I will talk to you soon.